gonna be a two-part of it. There will be two parts of my talk. One is gonna be WKU, which I will start in a bit. But first, I just wanna talk about this, this self-adjoint extension that we need to deal with for the one-dimensional part of our problem, so that we make sure that actually, the Hamiltonian that we have wrote over here actually makes sense in our sense as well. So, I think it was L in the notes, or maybe it's H, I don't know. Let's start with L for now. This was our problem. And in the spherical form, we had L square R minus 2 over R dr plus L plus 1 R squared plus 1 over R. Right, and we write this as U. I'm gonna say what U is negative R squared plus 1 over R plus L plus 1 over R squared U minus, where U is dividing by R. So I also looked at the solutions, but this is what I did. Well, if these are all HLs, but I'm already setting the notes that H0 is not essentially self-adjoint or self-adjoint, whatever. And the reason is because it's not.
Which space?
I'm gonna take C0 infinity.
Which Hilbert space is ambient?
L2.
Because we have to be careful with the measure. Is it L to RDR or L to ER? What is the measure? What is the measure of the half-life? R?
Oh,
R or
so here I see here. Oh, I mean, over here L2R, of course, but here we're just gonna be in L2 because we already divided.
what is L to R?
So you will have X squared, R squared, ER, big finite, 0 to
Yeah, and L2 is just measure TR. Right, so the L2 is integral X squared over TR.
VR. Okay.
No, for your H after conjugation. Your H after conjugation, your HL. This one is what's the ambient? Yeah.
I just heard it right. U is
Dividing by R. So because it is in the limit circle case at 0. And we already know it is in the limit point case at infinity. So this already tells us that my deficiency indices are 1, 1, or the kernel of H star plus and minus I is just 1, where H0 star plus and minus is 1. So I looked at what is the solution of these guys. Huh? Oh yeah, the dimension. Yes. So what I did over here for H0, actually I did a change of variable. I said R is equal X over 2 negative 2 root C, and I was finding the solutions of these, and I take positive, and my cutoff is from 0 to 5. That's not really too important.
Just a little.
Uh-huh.
So maybe if I were to, this will it not be, or can you look at it on, can you impose directly condition? So you look at the function.
Over here,
Yes.
I mean, actually what happened is, this is what I did. I basically did this change of variable and it turned this Vitaka equation, and then we already know the solution of that.
Mhm.
Because if you take this thing, and if you just take that,
Mhm.
R is equal, so here my equation depends on R, and if you take R is equal X to over root minus C, then this exactly turns to this equation. B squared F over dx squared plus -1/4 plus -1 over sigma 1 over X F is equal to. And that's exactly the Vitaka equation. For, huh? Oh, yeah, this is gonna be, because I later take it as real, and then it turned out what we had. What's gonna look like. So then we know the solutions, right? So this one, so my solutions are gonna come X. Well, actually, I can just write in terms of M and Z functions, so I will have R Z, and that is gonna be 1 over 2 root Z, comma 1/2 times 2 root Z X. And I will have the other one, which is the W, it's like a W1, and that's gonna look like, again. And then I use MATLAB. So what I did is, I take that, I plug root plus and minus I, and I checked out how they look like at infinity. And this was X zero, I'm sorry. So the around zero, how they were behaving. So I have when Z is I had this one is looking like some constant, which is M, right? X plus or X squared. And my Y2X is looking like some constant Y minus low plus all X. And that's why I told you that these coefficients, their coefficients are the same. Then, and it's infinity, none of them is L2. So then I said, okay, this solution actually plus and minus is minus I should like, let me don't write it this way. So my F is like a linear combination of these.
So, you don't have to spend money on H0 star.
Yeah,
This is the adjoint, it has the same formula, but it is completely different than H0, because we can't just put it on any domain we want. H0, the domain of H0 star is given completely.
exactly. Now I'm gonna give how those are gonna come.
the ambient space, that's why I asked, is L2 dr, L2 relative to dr. So I think you selected because you had to one of two solutions, because you have a fundamental system of two. Isn't one exponentially growing, which is out because it's not L2? The other one you pick, correct?
You see, that's actually why I asked him. None of them was two at infinity to me.
Then they don't lie in the domain of H star, and therefore they are not in the kernel. You see, what is kernel H star plus minus I? By definition, all F in the domain of H0 star, such that H0 star F is plus or minus plus IF.
So I agree with that, but then what I thought is this: there should be at least one in L2 at infinity.
Correct.
Because and that's what I thought, that should be actually their linear combination. Why? It has to be because it's limits point case at infinity. So there should be one combination such that that's gonna have a cancellation, and it has to be in L2. Am I wrong?
No, I'm just trying to understand. So you are still working with general Z because you wrote let's.
No, I take
Z,
the and I.
You plug in Z to the button, so then it means you're looking at the kernel of H0 star minus I.
Yeah.
So absolutely, there must be an L2 solution.
I agree, and that's actually the seed that we also needed as a this function you were giving a name.
That's the dialectic part.
Yes, exactly.
Maybe just because, so how do you get y1? Or you just plug it in and then it vanishes at 0?
Yeah, it's exactly this Taylor expansion of this because I am and W functions when you plug Z is the exact number that I asked you over here, which were both at infinity, both not L2. So that's what I think. So there could be at least one L2 function, and it has to come as a linear combination of these.
That the fact that they are both not in L2, you could perhaps find one function that makes the sum.
Yes,
between L2.
yeah, that's what I had in my mind.
Yeah.
So, and you see the expansions, like you see the self-adjoint extension of this. So basically, this is what we're looking for. When I look for the self-adjoint extension of H0, I'm actually looking for H0 star. They are restricted in a domain. Let's give it in this theta. So these domains, the thetas, they're supposed to actually look like some phi 0 plus, let's call this phi plus some constant time phi plus e to the I theta times the same constant times phi minus, where phi minus will be I will write about phi minus, okay? And so phi 0 is gonna be in the core. So basically phi plus is the solution to H minus I equals 0 star. And phi minus is the solution to H star plus phi 0. So they're conjugate to each other. So these are all the self-adjoint extensions. You basically just rotate it. And theta is 0 to 5. This is one representation.
Here you already choose the L2. Here you already choose L2.
Yes, so this has to be in output. But for for the self-adjoint extension, our problem is 0. So that's why I only write the 0 expansion, because that's what we will need.
Question. Can you say a word about where does the steep data come from? Why? This is an amazing thing. Why do we get all? So can you explain the role of steep data? Is this crime formula? How do we get?
Yeah, this is the crime formula, yes. How does the proof come?
No, don't worry about it. Okay. Thank you.
Yeah, this is the crunch formula, yeah, and you can find it in actually a lot of books. If you are heard of, if you really want to see. And so one of them is the solvable quantum systems. I think that's what I. Oh, also Reed and Simon has.
Right, and sorry, so in your definition, so you have P naught,
Which is
correctly
in,
supported. Then you have C times the combination of P plus and P minus.
no, actually not exactly. You see, you just rotate this because there is a circle. You see, you just take. You take the solution over here and then you take the lower one and then you rotate it. That's what you add in your domain. So these are all extensions.
But it's so it's the same C, so it's C times P plus E to the I theta P minus.
Yeah, these are the same concept.
And so then, but so this would be any linear combination, except that you want to force that P plus, you can always divide by the coefficient in front of P plus. Okay. It's not just your circle, you're forcing there is a P plus component.
So I think the way to understand this defines a non-closed subspace of L2 on the half-line D. And it is given by adding one dimension to what people call the chord, which is our prerogative to choose. We can choose compactly supported smooth functions away from 0 and infinity. And that's the core. Clearly, this is not closed, but notice that we add a one dimension, we add a line to this chord. What's the line? You take phi plus I theta phi minus, and then you multiply that by any complex constant C1. The picture is just this non-closed subspace. It's up to us to choose, and this is, one has to get used to this, and then you add the line to it. Now, what's amazing is, can you say how H0 acts on D theta? That's a definition. We now declare what H0 does on D theta. And then we have to take the closure in the graph norm, and that's how we end up with a self-adjoint operator that satisfies the boundary condition that's 0, which depends on theta. No?
Yeah.
So how does H0 act on D theta?
So if you add C plus. So from here,
Fine, because we're in the core, H0 by 0. H0 by 0 is well defined because it's a smooth function. So we just write H0 by 0.
okay, so I thought that's gonna be something, and then here you will have C times I by 0, and then here you will have plus E to the I theta I by.
Yeah, so exactly H0 on phi plus we declare to be, what is it, minus I by 0, plus I by 0, one of these. And the other one is minus.
Yes.
Yeah. To the definition.
Yeah.
We just say what H0 does in that line that we added to the core. And now we have to take the closure of this, because you see, if we had taken another core, for example, C2 functions that vanish rapidly at 0, rapidly at infinity, we would get a different D theta, but we would get the same closure in the graph.
Just a much simpler question is just that if I wanted to add a circle made of P plus and P minus, it would be more like cos theta P plus I sin theta continuous.
You mean you want to add a two-dimensional subspace to the core? We're adding a one-dimensional.
No. So C is in factor.
It's outside.
Is outside. But this, I mean, it's just the way to define it. Either it's 1 plus E to the I sigma Y. For
Yeah,
first
so
time.
logically, all self-adjoint extension because of the Cayley transform have to be a circle. Once you have division the indices 1, 1. The manifold of its self-adjoint extension is a circle with logic.
No,
It's exactly the E to the L. Because you are looking at all possible unitary extensions of the kilograms meters that you look.
So for Schrödinger operators, n plus and n minus can only be at most one. No, can we be
In one D, they're not one, as soon as you go to higher D, they just become. You have infinitely many, extensions, not infinitely many boundary conditions that we can.
I see it. And so in that case, you would have a more complicated construction, so that you would have to add it.
That's not complicated, but this is never actually work.
So this is a feature of one dimension.
This is because we have a one-dimensional kernel of H0 star doesn't decide.
But I think,
Efficiency indices are not equal, they are not. So they must be equal, that's the, the. That's what last night's dinner.
so as long as n plus and n minus are equal to each other, you should be able to find the self-adjoint extension. That's what I know. And the Klein formula also actually works, as I saw, there is also formula for also like if you have to have multiple.
It's still two, but if this needed is two, both of these two, then maybe you have to add a plane.
Yeah.
Or maybe it doesn't, that's what I'm saying, so they're looking, so if you can explain this better. Okay, all right.
But, well, just to that point, so for one D Schrödinger operators, the efficiency indices can be at most one, is that
No.
correct?
So depending on, I'm sorry, like depending on the order of your equation, for Schrödinger, you are two order, like the order is two. So how many linearly independent solutions do you have? Two. So you check out zero, how many of them L2 or not L2, and then you check around infinity, how many of them are in L2 or not L2. So if both of them are not L2, then you are limit circle case in both cases. So your deficiency indices are 2, 2. If at least one of them is limit point, then you have to be 1, 1. If both are limit point, then you are already self-adjoint.
So, sorry, and then so efficiency indices, so basically the deficiency indices measure, and so in this special case, Schrödinger operators in 1D, the deficiency indices basically measure how many limit circle cases you're
Why
in.
are they called deficiency? They measure the deficiency of a symmetric operator to be essentially self-adjoint. If it goes zero, and you take the closure in the graph, none of the symmetric is self-adjoint.
Right.
And then the more, if it's one, then it will show us that you get logically a circle, which is not surprising because remember what's in the ancient textbooks at zero, we just look at y of 0 cosine theta plus y prime of 0 sine theta equals 0. But there you have this circle. So you look at all possible linear combinations, it's just to project the angle that y prime makes with the x-axis of the 0.
But if your limit point at 0 and infinity, then you have a
If you
self-adjoint.
make it from 0 to infinity, that's equivalent to saying that the essential self-adjoint. Remember that is computationally this means we have a resolvement without having to add boundary conditions. Sorry.
So this is one representation of all the domains of the self-adjoint H, like, yeah. And there is also another representation that you must have seen in one of the papers that Hamiltonian just suggested to read about the how to find the Greens kernel, and that looks like this. And that is written in terms of the boundary condition. So we look for basically those G's, they are also in alpha such that J from G prime 0 is alpha times G. And here again, your alphas are all one. So again, this defines again a circle, and that's why we are in limit circle case. Now you see, these are our G's. Basically, these are how our G's are gonna look like. And I know how this plus and minus their behavior at 0. So then this is what I want to do. I either will have logarithm in my domain, or I will not have the logarithm in my domain. Either with this e to the I theta, I will cancel the logarithm term here and here, and that will give me one self-adjoint extension. And if I cannot really cancel it, so that will correspond to another self-adjoint extension, if you look at over here. Because the important part is what is happening at 0, right? So let me look at here. You see, these are my terms. If I just check out G X, they're gonna look like phi 0 plus C5 plus C5 minus. Now, if I pick, let me write this so that I will be clear. If I pick my e to the I theta such that the 1 minus log R term cancels from plus and minus part, then in fact what is going to happen is my G is going to satisfy G0 is 0, right? Because this term is going to cancel, so at 0 this is gonna work, and its prime is going to correspond some number. I mean, like depending on what you pick here. So that's why this actually corresponds over here when your alpha is infinity. Maybe I was wrong here, right? This is not alpha. Sorry, maybe this cosine and sine, it's gonna relate it to equal 1. Let's have this alpha like this. These are all tangent values actually. I put it wrong there. So this is one of them. And if it doesn't cancel, if your e to the r theta is not picked in that way, if not, in that case, again, the same G, if we take this G, then in that case, your G0 will be some constant, and G prime 0 will be infinity. And then that's going to correspond when your alpha is 0. So that's why you have two self-adjoint expansions. One of them is when alpha is equal infinity, and the other one is alpha is equal 0. And in fact, this is, you see, this is a unique one, and this is actually what we are looking for. Because
This zero is longer. So the ratio is.
oh, that makes sense, right? That's actually this is x log x, right? That's x log x. Yes, right? We saw here it was 1 over x plus log x, and then when you multiply, it's going to be a constant times x log x. I think my notes are wrong. So in that case, I'm right. So that's why we have two self-adjoint extensions. One of them is when alpha is infinity, and the other one is when alpha is 0. And this is actually what we are going to take, because over here, my domain G's are actually in W2 and 2, and that's what I expect, because we start from the problem from Rn, and we already have a resolvent over there, and that resolvent maps L2 to H2. So that's why we already expect our domain to be in W2. These are not over there because of this x log x term in it, and then these are in W2 too because we already removed. So that's why if you want to find a kernel over there, what you need to take is your domain is this one, in which your cosine alpha will be 0, right? That's what you need to consider and extend, find your green function according to that. You are looking as if I did something wrong.
Confusing to me, maybe I'm missing this. So you have, what do you mean by if not? So if you're not canceling the law,
Yeah,
right?
then you will have these.
But how can we, shouldn't we have infinitely many choices of alpha, but not infinity? You said we have one choice of alpha, which agrees with the formula,
Yes, that's what I think. I think there are two self-adjoint extensions.
but they have to be infinitely many. It's the formula circle. You said the criterion says that data gives us all possible self-adjoints.
So is it possible that even though you are two different self-adjoint extensions on the boundary that you convince? So the only thing that will be different, you see what I'm thinking, the only thing that will be different, of course, the C1. The C1 is going to change. This is going to be always infinity. And that will not really change my alpha, but maybe even though these are given a different self-adjoint extensions, their boundary conditions are going to be the same. But to me, that doesn't make sense. I think
Maybe say this.
but whichever we're taking is very clear. This is for sure, this is what we're looking for.
It's that the formulation of the alpha is meaningless for the one of the argument and shown because it is too singular at 0. So you cannot make sense of the initial boundary problem at 0 for the concept of R. So you would have to take a different line. And then you will recover the circle. You must have a circle. The grand formula said that. And yeah, so we cannot do the usual game with cosine theta g prime 0 plus
So you
sine
keep your
theta
point.
g of 0 equals 0. That doesn't work because of the one of the r square. So you correctly once identified the one,
That's where
the
the work.
only one that we must choose so that we get our historical clear, because otherwise we don't get our unity proof. Very good.
So that means if you want to understand this part better, we gotta pick another reference point.
I think that alpha should be infinity in that definition also. Because G prime is infinity. G0 is some number, so you have to have alpha infinity as well.
No, it's supposed to be 0.
But like, I understand your logic, but so it seems that this formulation you just said probably just doesn't is not meaningful here.
Oh, this formulation, oh yeah, this formulation is, we agreed that it's not making sense. But this totally makes sense, I can say that.
Yes.
Yeah, because that also corresponds to Friedrich's extension. But here, yeah, but I think I calculated this and I agreed that it was gonna be the 0. So this is infinity. And this is a constant. So you are saying that has, or maybe this was to 0. I'm sorry.
Both of them are infinity by this equation. But the way you wrote it, G prime is equal to alpha G, that's both of them should correspond to infinity. So I think that somehow this
doesn't work.
doesn't work.
Okay. It doesn't work. This is what we're looking for.
So this is an excellent because it shows us that we have to be careful with the singularity of one of our zeros. We can't defy iteration of zeros. If we had one of a root r, then all of this would work.
Yeah.
Should we take a break and if we do argometry after lunch, or you want to do argometry now?
I can do after lunch.
And it's up to the so.
No, Okay, let's just read that.
Okay.
So another way to pick your domain would have been to use the form domain
What is it?
or the Frederick extension.
Yeah, this corresponds to Frederick's extension exactly. So it's, so basically our green, our resolvent operator will be exactly reduced from the higher dimensional one. Like a regular resolvent form, because we know that this is in higher dimension, this is self-adjoint, because you don't have it really like a zero problem somehow. So whatever the resolvent is gonna reduce from here has to match with this resolvent. And that's gonna be the Frederick's extension resolvent.
And
You
is
see.
there a way to see that from the point of view of the form? So if you look at HF, F, then the only way for this to be finite would force you to be 0 at 0, because otherwise you're integrating 1 over R.
I don't
You asked about the form domain, so the energy, the quadratic form, HFF.
Exactly.
So
Is it
that's
always
so negative, and that gives us a negative.
So it's always going to give you a domain on which your operator will be self-adjoint?
Well, yeah, so if you, how does it work? Your quadratic form is defined from below, you can assume greater than 0. Then you can define, you have to be careful with this, because on first side that controls one derivative. Right? That's H1, not H2, that is H2.
So your domain is
This is not so straightforward. There is a procedure to say that you can use the quadratic form to define a boundary condition at 0, but you still have to operate on the level of H2. So for example, if you do this just for the standard minus y double prime, you take the free Laplacian of the half prime, and then you take the form, which is the H1 word. I think the biggest extension will give you the theoretical boundary condition.
It gives the respect, and again, this is gonna come.
And why is that? Because the closure, you have to make the closure, you start from functions that
automatically supported, and then
vanish
the
is
closure,
zero, take the closure, you get the
closure is expected at norm,
and then automatically the take the closure of the quadratic form of the function that are completely supported and then 0, and you get h from 0, you get 0 from 5.
Yeah, that's what just that allow you to always be sure that you can, like the point is to, after plugging or be sure that you can use the formulas for the distorted Fourier transform. At least the Frederick extension, when it exists, it gives you a domain where you will be self-adjoint for free.
Yeah. That's why everybody thinks of this extension. This exists. As long as the quadratic form is covered.
But in case it was another way to make it self-adjoint, then this would have given to you as well. And you would have also distorted for your transform on this other domain. So in some sense, this is more general because it really gives you all of the possible ways to do it.
But they could never come from the R3 operator. They only want to come from the R3 operators.
Right, great. So 30, we will come back at 2. Yeah, that should be enough time.
Yeah. No, I thought that's, you meant the other way around.
Well,
There was too much time.
yeah, no, this is, I mean, it's enough time in the afternoon.
Yeah.
I think it was regular cases. Very good. I mean, they should, I think, respond.
So we should stop.